In this lecture, I will discuss page replacement as it is used in the virtual memory subsystem. I will discuss global and local page replacement, page table entries that support page replacement, and a number of classical page replacement algorithms. Whenever there is a demand for memory that is greater than the actual amount of physical RAM installed on the system, the operating system must determine which pages will be kept in memory and which pages will be swapped out to disk. When memory frame contents are swapped out to disk, the operating system needs to find a page of memory that is not currently in use. Furthermore, in an ideal case, the operating system should also pick a page that will not be used for some time, so as to reduce the total number of page swaps. In order for the page swapper to operate, some additional data must be kept about each page, including whether or not the page has been referenced and whether or not the page has been altered since it was last swapped into RAM. Decisions regarding page swaps can be made globally or locally. With global replacement, any page in the system is a potential candidate to be swapped out in favor of another page. While simpler to implement, global page replacement does allow processes to steal memory frames from each other. On the other hand, local replacement policies allocate a limited number of frames to each process. When a process exceeds its frame allocation, only frames belonging to that process are selected for replacement. Implementing a local page replacement algorithm is more complex than it seems on the surface, largely due to Bellidy's anomaly. Allocating more frames to a process does not necessarily reduce the number of page faults that occur as a result of that process. In fact, with some replacement algorithms, increasing the number of available frames actually increases the number of page faults that occur. At the opposite extreme, allocation of too few memory frames to a process also increases the number of page faults. Without enough physical memory, processes will spend more time page faulting, or swapping, than they will spend executing. The goal with a local replacement algorithm is to find an optimal working set for each process. This working set is the minimum number of frames that a process actually requires in order to execute to some desired level of efficiency. Regardless of whether global or local replacement policies are chosen, the operating system needs a few pieces of information to implement page swapping correctly. First, the operating system needs to know whether or not a page that is currently in memory has been referenced by a process. Pages that are loaded but unused might be more ideal candidates to be swapped out to the backing store. The second piece of information that needs to be stored in the page table is the dirty bit. This bit is set to 1 whenever a process writes to a page, which lets the operating system know that the copy of the memory frame contents on the backing store needs to be updated whenever the page is swapped out. Keep in mind that on systems with hardware-managed page tables, such as the x86 and x86-64 platforms, the MMU updates these bits automatically. Whenever a page fault occurs, the operating system must locate the desired page on the backing store. Then it must find a free frame in RAM into which the page can be loaded. If no memory frames are free, the operating system must select a victim frame to be swapped out to the backing store. The algorithm that is run to determine which frame will be the victim is called a page replacement algorithm. Page replacement algorithms ideally should minimize the total number of page faults in the running system in order to maximize system performance. Let's take a look at several classic page replacement algorithms. The first classical page replacement algorithm we will consider is the random algorithm. Whenever a page swap is required, this algorithm simply picks a victim frame at random. In practice, this random selection often picks a page that will be needed in the near future, leading to another page fault in a short time period. As such, it is not effective for minimizing page faults. Another ineffective algorithm is to select the oldest page, or the page that has been in memory for the longest period of time. Unfortunately, this page could be frequently accessed, so if it is swapped out, another page fault could be triggered in a short period of time to bring it back into memory. Somewhat counterintuitively, selecting the frame that has been accessed the least frequently is also ineffective. A page that is used relatively infrequently might still be used regularly, which would lead to another page fault to bring this frame back into RAM. The most frequently used algorithm picks whichever frame is being used the most and selects that frame to be swapped out to the backing store. This is a completely stupid idea, since this page is likely to be accessed again shortly after it is swapped out. A good algorithm for choosing victim frames is the least recently used, or LRU algorithm. This algorithm selects the victim frame that has not been accessed for the longest period of time. Unfortunately, with current hardware, there is no good way to track the last memory access time. Tracking every access in software would be a terrible idea, since such a scheme would require an interrupt on every memory access. Thus, it is impractical to implement LRU directly. Most implemented page replacement algorithms are approximations of LRU, however. Theoretically, the optimal algorithm, or OPT, is the best page replacement algorithm to use. With this algorithm, the operating system picks a frame that will not be accessed for the longest period of time as the victim, delaying a future page fault related to the corresponding page for as long as possible. A mathematical proof exists showing that OPT is the best possible page replacement algorithm. Unfortunately, OPT is also impossible to implement, since it must be able to predict all memory accesses ahead of time. As such, we are left with LRU approximation algorithms such as the Not Used Recently, or NUR algorithm. NUR tracks frame accesses using a combination of the reference bit, dirty bit, and/or an age counter. This algorithm produces reasonable performance in actual implementations.